I thank each one of you for watching my videos and encouraging me. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We now discuss the solution of a problem that appeared in the CSIR National Eligibility Test held in the month of December 2023. This question is from the section Real Analysis and it is related to the discontinuities of given functions in the question paper. This question is placed in part C, which is a multiple select question. There can be more than one answer and the question carries 4.75 marks. The question ID is 704067 and this question is suitable for all these examinations also. Right. The given question is, which of the following statements are true? Option 1. The function f from R to R, where R is the set of real numbers, defined by f of x is equal to bracket x or box x or GAF of x multiplied by sine 1 by x for x not equal to 0, f of x is equal to 0 for x is equal to 0 has a discontinuity at 0 which is removable. Option 2. The function f from the open 0 to the function f from the closed 0 to open infinity, that is a semi-closed interval, to R defined by f of x is equal to sine of log x for x not equal to 0, f of x is equal to 0 for x is equal to 0 has a discontinuity at 0 which is not removable. Option 3. The function f from R to R defined by f of x is equal to e power 1 by x for x less than 0. F of x is equal to e to the power of 1 by x plus 1 for x greater than or equal to 0 has a jump discontinuity at 0. Option 4. Two functions f, g from the closed interval 0, 1 to R be two functions of bounded variation, then the product of g has at most countably many discontinuities. So this question is framed based on the definitions of removable discontinuity and the jump discontinuities. We now discuss the solution of the problem in detail by taking the options one after the other. Option 1. The function f from R to R defined by f of x is equal to bracket x, that is GAF of x sine 1 by x for x not equal to 0, f of x is equal to 0 for x is equal to 0 has a discontinuity at 0 which is removable. Now the question is x is equal to 0 a removable discontinuity of f of x? If x is equal to 0 is a removable discontinuity of f of x, then both the left limit and right limit about x is equal to 0 of the function fx exists and they are equal but not equal to the value of the function f at 0 then x is equal to 0 is a removable discontinuity. That is, limit x tends to 0 plus f of x, LHL, limit is equal to limit x tends to 0 minus of f of x, left hand derivative, this is left hand derivative, this is right hand derivative. So this is RHL is equal to LHL, right? And that's not equal to f of 0. So both of them exist, they are equal but not equal to f of 0. Then x is equal to 0 is a removable discontinuity. Limit x tends to 0 plus of f of x, right? So that is equal to limit x tends to 0 plus of bracket x sine 1 by x is equal to 0. Remember, limit x tends to 0 plus of bracket x is x is 0 plus some h which is positive as h tends to 0, right? So that means the bracket x as x tends to 0 plus is 0. It is the bracket x is what? It is the greatest integer not exceeding x. As x tends to 0 plus, it is 0. So the limit exists. Limit x tends to 0 minus of f of x is limit x tends to 0 minus of bracket x into sine 1 by x. Limit x tends to 0 minus of bracket x is minus 1. And that is equal to minus 1 into limit x tends to 0 minus of sine 1 by x. This does not exist. This does not exist. So therefore, on the whole, the limit x tends to 0 minus f of x does not exist. And to be removed, to have removable discontinuity at x is equal to 0, both the LHL and RHL must exist. And they are equal but not equal to f of 0. It is not so here. Therefore, x is equal to 0 is not a removable discontinuity of f of x. So the option 1 is not true. In the option 1 it is given it is a removable discontinuity, but here we have seen it is not. Option 1 is not true. Right. We move on to the next option. Option 2. The function f from closed 0 to open infinity, semi-closed interval, to r defined by f of x is equal to sine of log of x for x not equal to 0 is equal to 0 for x is equal to 0 has a discontinuity at 0 which is not removable. We have already seen if x is equal to 0 is a removable discontinuity of f of x, then limit x tends to 0 plus f of x not equal to f of 0, since the domain of f is the semi-closed interval, that is closed 0 to open infinity interval. So you need not talk about limit x tends to 0 minus of f of x, because it is the closed 0 is here, so it is sufficient that we talk about limit x tends to 0 plus of f of x exists and not equal to the value of f of 0, right? It is sufficient if you do 1, because limit x tends to 0 minus f of x is not included, because the interval is the semi-closed interval 0 to open infinity, right? Now limit x tends to 0 plus of f of x is equal to limit x tends to 0 plus of sine of log of x. This is equal to sine of the limit we can go inside, because sine x is continuous. So sine of limit x tends to 0 plus of log x, right? Will it exist? So this does not exist, because limit x tends to 0 plus log x does not exist. Therefore, x is equal to 0 is not a removable discontinuity of f of x. So that is what is precisely given in option 2. Therefore, option 2 is true. Right. We move on to the next option. Option 3. The function f from R to R defined by f of x is equal to e to the power of 1 by x for x less than 0. For x greater than or equal to 0, e to the power of 1 by x plus 1 has a jump discontinuity at 0. So, x is equal to 0 is a jump discontinuity of f of x if limit extends to 0 plus of f of x and limit extends to 0 minus of f of x exists. That means both LHL, RHL about x is equal to 0 exists and are not equal, then it is called a jump discontinuity. Limit extends to 0 plus of f of x is equal to limit extends to 0 plus of 1 by x plus 1 exponential, and 1 by exponential is continuous. Therefore, it is e to the power of 1 by 0 plus 1, 1. So, it is e. Limit extends to 0 minus of f of x is equal to limit extends to 0 minus of e to the power of 1 by x because of continuity. Limit h tends to 0, e to the power of 1 by 0 minus h. That is limit h tends to 0, e to the power of minus 1 by h. That is limit h tends to 0, 1 by e to the power of 1 by h. This is 0. As h tends to 0, 1 by h tends to infinity, e to the power of infinity, 1 by infinity is 0. Agreed. So both exist. LHL and RHL both exist, but they are not equal. Therefore, it is a jump discontinuity. Right? They exist, they are not equal. Thus, x is equal to 0 is a jump discontinuity of f of x, which is precisely given in the option 3. Therefore, option 3 is true. Right. So far, except 1, option 1 was false, was not true. 2, 3 are true. Right. Let's move on to option 4. Option 4. F, G, closed interval 0, 1 to R be two functions of bounded variation, then the product Fg has at most countably many discontinuities. Right. After a long time, question on bounded variation is appearing. Right. We have two functions Fg from the closed interval 0, 1 to R are functions of bounded variation. Right. Let df, dg, dfg be the sets of discontinuities of f, g and fg respectively. That is, df is a subset of the closed interval 0 to 1 and the elements of df are the discontinuities of f. Now, we recall a result about functions of bounded variation regarding the sets of discontinuities of functions of bounded variation. Recall, if f closed interval ab to r is a function of bounded variation on the closed interval ab, then the points of discontinuities of f form a countable set. So, what is given to us? F and g are functions of bounded variation. Therefore, by the above result, df and dg are countable sets. Agreed. And you note down a point here. df union dg is also a countable set because it is the union of two countable sets, which we require later. Now, f is continuous at x, g is continuous at x, will imply fg is continuous at x. So, f is continuous at x means x is not a point of discontinuity. Therefore, x belongs to df complement. And g is continuous at x. That means x is not a discontinuity. Therefore, x belongs to dg complement. And so also fg is continuous at x, x belongs to d of fg complement. That is, x belongs to df complement and x belongs to dg complement, and that implies x belongs to dfg complement. X belongs to df complement and x belongs to dg complement will imply x belongs to df complement intersection dg complement implies x belongs to dfg complement. Use the De Morgan's law here. X belongs to df complement intersection dg complement will imply x belongs to df complement union df union dg complement. X belongs to df complement intersection dg complement. Use the De Morgan's law. Then you will get x belongs to df complement df union dg complement. That will imply x belongs to dfg complement. So df union dg complement is contained in dfg complement. Take the complements on both sides, it will get reversed. It will imply dfg is contained in df union dg. I have already told you df union dg is also countable since df and dg are countable sets. So thus dfg is a subset of a countable set. When dfg is a subset of countable set, then dfg is either finite or a countably infinite. This implies dfg is at most countable. Either it is finite or countably infinite. Therefore, dfg is at most countable since df union dg is a countable set. So that is what is precisely given that. Therefore, the product fg has at most countably many discontinuities. Thus, option 4 is also true. Summarizing all the options, we have options 2, 3, 4 are true. Therefore, the answer to this question is options 2, 3 and 4. That is the detailed discussion of the solution of the given problem from the real analysis, which is related to the discontinuities of first kind of given 4 functions. Agreed. This is definitely an easy problem, but it will take time because all three options are true here. I am sure that you have understood the solution of this problem. Thank you for watching my video now. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. We hope to meet you once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.